Here the first figure represents dry soil. So when we apply pressure on dry soil, this pressure is transferred from one solid particle to another one through the point of contact. So these are the point of contacts through which pressure is transferred. This is an imaginary line which passes through point of contacts. This line is assumed as a straight line because the size of the undulations are very small. So this line is assumed as straight line. Hence the pressure will be equal to applied load upon area along that imaginary straight line. So for in case of dry soil, the entire pressure will be taken by the solid particles only. On the other hand, if the soil is saturated, so here the second figure represents saturated soil. So when soil is saturated, some part of the applied pressure will be shared by water and some part of pressure will be shared by solid particle. So if we segregate water from the solid particles, then the representation will be like this. These are solids and this is water in saturated soil. So when we apply pressure of say delta sigma 1, some part of the pressure will be shared by water and some part of the pressure will be shared by solid particles. The pressure shared by water is represented as U bar and the pressure which is shared by solid particles is represented as delta sigma 1 bar. It is also called as effective pressure. So when we apply pressure on the saturated soil, then immediately after the application, that means at time t is equal to 0, the entire pressure is taken up by the water. Means we have delta sigma 1 equal to U bar plus delta sigma 1 bar. But at time t equal to 0, as the entire pressure is shared by water, the value of delta sigma 1 bar, that is effective pressure, becomes 0. Hence delta sigma 1 become equal to U bar. This pressure is called as excess pore water pressure. Excess pore water pressure. So here the water is under pressure which is equal to applied pressure and the water which is in surrounding area doesn't have any pressure or is under lower pressure. Hence hydraulic gradient is developed and water starts escaping from the area of higher pressure towards the area of lower pressure. Because of this, the pressure which was initially shared by water is transferred to the solid particles. That's why as the time progresses, more and more water escapes and this escaping water transfer the pressure to the solid particles. Hence, gradually the value of U bar get decreased and value of delta sigma 1 bar gets increased. At time t equal to Tf, the entire pressure is shared by solid particles only. Hence, value of U bar becomes equal to 0. Hence, delta sigma 1 bar becomes equal to delta sigma 1 bar. Hence, delta sigma 1 becomes equal to delta sigma 1 bar. Hence, total applied pressure becomes equal to effective pressure. So, as the time progresses, the effective stress increases and volume of soil get decreased. Suppose This is our soil mass. These are the solids. This is water. So as effective stress increases, more and more water get escape. So because of this, the volume of the soil mass get decreased. This decrease in volume is represented in terms of decrease in void ratio. Now we know the formula for void ratio. It is volume of voids to the volume of solids. So suppose this height represents volume of voids and this height represents volume of solids. So as the water escapes, the volume of voids decrease whereas volume of solids remains constant. So eventually value of E gets decreased. So if we draw a plot of E versus T, then at T equal to 0, the value of void ratio will be maximum. As the time progresses, it will gradually decrease, and at time T equal to Tf, where entire pressure is transferred as effective pressure, that is delta sigma 1 is equal to delta sigma 1 bar, void ratio will be minimum, that means E will be equal to E minimum. So this is the time versus void ratio plot for a particular load, say delta sigma 1. So as I have said, at time t equal to 0, the value of void ratio is maximum. As the time progresses, the void ratio gradually decreases, and at time t equal to Tf, where entire pore water pressure is dissipated and effective pressure is equal to applied pressure, then the value of void ratio is minimum at this point. So we can see that for pressure delta sigma 1, the value of minimum void ratio is EF1. If we increase the pressure to delta sigma 2, the value of minimum void ratio will get decreased to say EF2. If we further increase the pressure to delta sigma 3, then the value of minimum void ratio will also get decreased and it will become say EF3. So if we plot a graph of delta sigma, that is pressure versus minimum void ratio, then the graph will be like this. Means lower the pressure, more will be the final void ratio, and more the pressure, lower will be the final void ratio. So this is the plot we have discussed, which is between EF, that is final void ratio, versus pressure, that is delta sigma. So here also in this graph we can see that the lower value of the pressure is corresponding to higher value of final void ratio. As the value of effective pressure increases, the corresponding value of final void ratio gets decreases. Means soil tends to get more compressed with the increase in effective stress.